What if I told you that every single photograph you've ever seen of the Andromeda Galaxy is a lie? Not in the way you think. The lie isn't in what's visible. It's in what's missing. For over a century, we've been looking at our nearest galactic neighbor, thinking we knew its size. We measured it. We photographed it. We mapped it. Andromeda appeared as this beautiful spiral, floating in space, roughly 6 times wider than the full moon in our night sky. Scientists calculated it at about 220,000 light years across. Case closed, right? Wrong. Devastatingly, mind-bendingly wrong. In recent years, astronomers made a discovery so shocking that it forced us to rewrite the cosmic address of our galaxy. They found something that was there all along, invisible, surrounding Andromeda like a ghost. When they finally measured the true size of the Andromeda Galaxy, they discovered something that will change how you see the universe forever. Are you ready for this? The Andromeda Galaxy isn't 220,000 light years across. It's over 1 million light years in diameter. That's not a typo. Our nearest galactic neighbor is more than 4 times larger than we thought. And here's what will absolutely shatter your perception of reality. Andromeda's outer edge is already touching the Milky Way. Right now. This very second. We're not waiting for a collision in 4 billion years. We're already inside each other's cosmic embrace. You are, at this very moment, living inside the beginnings of the largest cosmic merger our region of space will ever witness. Before I show you how scientists discovered this, and what it means for Earth, for you, for everything you think you know about space, hit that like button and subscribe. This is going to be a journey, and I promise you'll never look at the night sky the same way again. Also, drop a comment telling me what country you're watching from, and what time it is for you right now. I want to see this global community come together as we explore one of the most profound discoveries in modern astronomy. Let's begin with what scientists thought they knew. To understand why this discovery is so revolutionary, we need to go back to 1924. That's when everything changed. Before that year, most astronomers believed the Milky Way was the entire universe. Everything we could see, they thought, existed within our one cosmic island. The fuzzy spiral patches in the sky? Just nebulae clouds of gas within our own galaxy. Then came Edwin Hubble. Not the telescope, the man. Working at the Mount Wilson Observatory in California, Hubble pointed the 100-inch Hooker telescope at one of these fuzzy patches, the Andromeda Nebula, as it was called then. He discovered something extraordinary. Within that fuzzy patch, he identified individual stars. Specifically, he found Cepheid variable stars that pulse with a regular rhythm, brightening and dimming in predictable patterns. Here's why this matters, and this is your first mind-blown moment of this journey. Cepheid variables are cosmic lighthouses. A brilliant astronomer named Henrietta Swan Leavitt had discovered in 1912 that these stars have a direct relationship between how bright they truly are and how fast they pulse. The faster they pulse, the brighter they actually are. If you know how bright something truly is, and you measure how bright it appears to be, you can calculate exactly how far away it is. Think of it like this. If you know a light bulb is 100 watts, but it looks dim to you, you know it must be far away. The dimmer it appears, the farther it is. Leavitt gave us the ruler to measure the universe. When Hubble measured those Cepheid variables in Andromeda, he calculated that this nebula was roughly 900,000 light years away. Today we know it's actually about 2.5 million light years distant, but the principle held. Andromeda was far beyond the boundaries of the Milky Way. The universe was suddenly unimaginably larger. We weren't alone. We weren't the universe. We were one galaxy among countless others. For the next several decades, astronomers refined their measurements of Andromeda. They mapped its spiral arms, counted its stars estimated at around 1 trillion, roughly double what the Milky Way contains. They measured its rotation, its mass, its chemical composition. By the late 20th century, the scientific consensus was clear. Andromeda was a massive spiral galaxy, clearly visible to the naked eye as a fuzzy oval patch in the constellation Andromeda, measuring approximately 220,000 light-years from edge to edge. To put that in perspective, if you could somehow travel at the speed of light 186,000 miles per second, fast enough to circle Earth 7 times in 1 second, it would take you 220,000 years to cross from one side of Andromeda to the other. That's incomprehensibly large. Light that left one edge of the galaxy before modern humans evolved would just now be reaching the other side. Scientists were satisfied. They had measured Andromeda. They understood it. It was the big sibling to our Milky Way, the dominant galaxy in what we call the local group, the collection of more than 50 galaxies bound together by gravity in our cosmic neighborhood. But they were looking at only part of the picture, the visible part. Galaxies, we've learned, are like icebergs. What you can see is just the tip. Spiral arms filled with billions of stars, glowing gas clouds where new stars are born, dark dust lanes where starlight is blocked. All of that is gorgeous, photogenic, and measurable. But it's not where most of the galaxy's matter actually resides. This brings us to one of the most profound mysteries in modern science: dark matter. Don't worry, we're going to take this step by step, because understanding dark matter is crucial to understanding what scientists discovered about Andromeda's true size. In the 1970s, astronomer Vera Rubin made observations that didn't make sense. She was measuring how fast stars orbit around the centers of galaxies. According to Newton's laws of gravity and everything we understood about physics, stars farther from the galactic center should orbit more slowly, just like planets farther from the sun orbit more slowly. Neptune takes 165 years to orbit the sun, while Mercury takes just 88 days. But Rubin discovered something shocking. Stars at the outer edges of galaxies were moving just as fast as stars closer to the center. Some were even moving faster. This shouldn't be possible unless there was more mass out there than we could see. Much more mass. Mass that didn't emit light. Mass that was invisible. Dark matter was the only explanation. Galaxies aren't just the stars and gas we can see. They're embedded in massive halos of invisible matter that extends far beyond the visible edges. This dark matter provides the extra gravity needed to keep those outer stars moving at their observed speeds. Think of it like this. Imagine watching someone swing a bucket of water in a circle over their head. The water doesn't fall out because the bucket is spinning fast enough. Now imagine the bucket is spinning much faster than it should, based on how heavy the water appears to be. You'd conclude there must be something invisible in the bucket, making it heavier. That's dark matter. For decades, scientists knew dark matter had to exist around Andromeda. They could calculate its gravitational effects. But dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all, except through gravity. It's invisible, undetectable except through its gravitational influence. So here's the question that haunted astronomers. If we can only see the bright parts of Andromeda, and we know there's a massive dark matter halo surrounding it, where does the galaxy actually end? How big is it really? The answer came from an unexpected source: a faint, wispy halo of extremely hot gas. In 2015, a team led by Nicholas Lenner from the University of Notre Dame published findings that would revolutionize our understanding of galactic structure. They weren't looking at Andromeda directly. Instead, they were studying something behind it. Here's where this gets clever, and this is going to blow your mind. Imagine you want to measure fog, but fog is almost transparent. How do you do it? You put a bright light behind the fog and measure how the light changes as it passes through. That's exactly what Lenner's team did with Andromeda. They used the Hubble Space Telescope to observe distant quasars incredibly bright, ancient objects at the edge of the observable universe, powered by supermassive black holes. These quasars are so bright, They can be seen across billions of light years. Leonard's team identified 43 quasars positioned behind Andromeda from our point of view. Then they analyzed the light from these quasars in extraordinary detail. Light is information. When light passes through gas, atoms in that gas absorb specific wavelengths, leaving dark lines in the spectrum, like a fingerprint. Different elements absorb different wavelengths. By analyzing which wavelengths were missing from the quasar light, scientists could identify what elements the light passed through. By measuring how much light was absorbed, they could determine how much gas was present. And by measuring how the wavelengths were shifted, called redshift and blueshift, they could determine how fast that gas was moving. What they found was extraordinary. Surrounding the visible disk of Andromeda, extending outward in all directions, was a massive halo of hot gas. Not just warm, but screaming hot hundreds of thousands to millions of degrees. Gas so hot that its atoms are stripped of their electrons, creating a plasma that emits X-rays and ultraviolet light, but so diffuse, so spread out, that it's essentially invisible unless you know how to look for it. This wasn't a small halo. It wasn't some minor addition to the galaxy's mass budget. This halo extended at least 300,000 light-years from Andromeda's center in some directions. That means the galaxy's true atmosphere, its corona of hot gas, was already larger than scientists thought the entire galaxy was. But they weren't done. Further observations pushed the boundaries even further. By 2020, researchers including Samantha Barrick and Nicholas Lenner published new findings. Using additional quasar observations and more sophisticated analysis techniques, they traced Andromeda's halo out to approximately 1.3 million light-years from the galaxy's center. That's a radius, meaning the diameter, the full size of Andromeda's gaseous halo, is roughly 2.6 million light-years. Let me pause here, because this number is so staggering, it's easy to miss its implications. The visible disk of Andromeda, the beautiful spiral you see in photographs, is about 220,000 light-years across. That's what we thought was the galaxy. The actual galaxy, including its halo, is nearly 12 times that size by volume. By volume, 12 times. If Andromeda were an iceberg, the part we thought was the galaxy would be just the tip poking above the water. The true structure, mostly invisible, extends into cosmic depths we never imagined. This halo contains mass equivalent to about half the mass of all the stars in Andromeda combined. We're talking about billions of solar masses of gas, most of it in the form of hot, ionized plasma. This is material left over from the galaxy's formation 10 billion years ago, enriched with heavy elements forged in stars that lived, died, and exploded as supernova, spreading their enriched ashes into the galactic halo. But here's what makes this discovery truly revolutionary. And this is your second major mind-blown moment. The Milky Way has a similar halo. Our galaxy isn't 100,000 light-years across, as the visible disk suggests. Our galaxy's halo extends roughly 500,000 to possibly 1 million light-years from the galactic center. Do the math. Andromeda's halo extends about 1.3 million light-years from its center. The Milky Way's halo extends roughly 500,000 to 1 million light-years from our center. The distance between Andromeda and the Milky Way's centers is approximately 2.5 million light-years. That means the outer edges of these halos are separated by perhaps just 100,000 to 700,000 light-years. Or they're already touching. Or they may have been overlapping for millions or billions of years already. We are not approaching Andromeda. We are already in the early stages of interaction. The galaxies are already beginning to merge. Think about what this means. Every time you look up at the night sky, you're not seeing two separate galaxies on a collision course. You're seeing two galaxies already beginning to blend, their outer atmospheres mixing in the vast darkness between visible stars. Atoms from Andromeda are in our solar system. Atoms from the Milky Way are in Andromeda's outer regions. The boundaries are not clear. The distinction is not clean. This realization forces us to reconsider what we mean by galaxy. Is a galaxy defined by its stars? Or by its gravitational influence? Or by the full extent of material that belongs to it? And here's the question that should keep you awake tonight. If Andromeda is this much larger than we thought, what else have we gotten wrong? You might be wondering, how did we miss something this massive? How do you overlook a halo of gas extending more than 1,000,000 light years? The answer reveals something profound about the nature of observation and the limits of human perception, even when aided by our most powerful instruments. The halo gas exists in what physicists call a Goldilocks zone of visibility. It's not quite hot enough and not quite cool enough to be easily detected. Let me explain. Cool gas, the kind in molecular clouds where stars form, is relatively easy to observe. It's dense enough that atoms bump into each other, interact, and emit radio waves we can detect with radio telescopes. Astronomers have mapped enormous clouds of cool hydrogen gas around galaxies using the 21-centimeter line, a specific radio frequency that neutral hydrogen emits. Extremely hot gas is also detectable. When gas reaches temperatures of millions of degrees, it emits X-rays powerfully enough to be detected by X-ray telescopes like NASA's Chandra X-ray Observatory. But Andromeda's halo gas exists primarily in an intermediate temperature range, hundreds of thousands of degrees. Hot enough that atoms are ionized, stripped of their electrons, so they don't emit the radio signals of cool neutral hydrogen, but not quite hot enough to emit X-rays strongly enough to be easily detected from 2.5 million light-years away. This temperature range is sometimes called the X-ray dim zone. Moreover, the gas is incredibly diffuse. We're talking about densities far lower than any vacuum we can create on Earth. In the best laboratory vacuums, you might have a few thousand atoms per cubic centimeter. In Andromeda's halo, there might be only 1 atom per 10 cubic centimeters. That's unimaginably thin. For comparison, the air you're breathing right now contains about 27 quintillion molecules per cubic centimeter 27, followed by 18 zeros. Think of it like this. Imagine trying to see fog when each fog droplet is separated from the next by the length of a football field. You'd look right through it. The fog would be real. It would have mass, but it would be effectively invisible. That's what astronomers were dealing with. The breakthrough came from using quasars as background light sources, a technique called absorption spectroscopy. This method is extraordinarily sensitive because you're not trying to see the faint glow of the gas itself. Instead, you're looking at how the gas affects light passing through it from behind. The brilliant astronomer who pioneered much of this work, Nicholas Lenner, compared it to looking at a stained glass window. You don't see the glass itself necessarily, but you see how it colors the light passing through it. Each element creates its own color pattern, its own absorption signature. Lenner's team found signatures of silicon, carbon, and oxygen elements that could only exist in ionized states at the temperatures they calculated, confirming the presence and temperature of the halo gas. But here's where it gets even more interesting. The quasar absorption technique only works if you happen to have a sufficiently bright quasar positioned behind the part of the galaxy you want to study. It's like needing a specific streetlight behind the fog to see it. For most of galactic astronomy's history, we simply didn't have enough known quasars with precise positions to use as background probes. The Hubble Space Telescope's sensitivity and the decades-long effort to catalog quasar positions made this technique feasible. There's another reason we missed the halo's extent: bias and expectation. Scientists had built models of how large galaxies should be based on visible matter and dark matter simulations. Those models predicted halos, yes, but not quite as extensive as what exists. When observations don't match expectations, the natural first reaction is often to question the observations. Are we interpreting the data correctly? Could there be contamination? Might the absorption be from something else along the line of sight? It took multiple independent observations, numerous quasars, different research teams, and years of careful analysis to confirm that yes, the halo really is this enormous. This is how science works. Not through individual eureka moments, but through the gradual accumulation of evidence that eventually overwhelms skepticism. The Nobel Prize-winning physicist Richard Feynman once said, "The first principle is that you must not fool yourself, and you are the easiest person to fool." Scientists studying Andromeda weren't trying to fool themselves, but they were constrained by what they expected to find based on previous measurements and theoretical models. The universe, as usual, turned out to be stranger and more magnificent than our models predicted. This discovery also highlights an uncomfortable truth about astronomy. We can only study what we can see, and there are many ways for things to be invisible. Dark matter is invisible because it doesn't interact with light at all. The halo gas was invisible because it was too diffuse and at the wrong temperature to easily detect. What else might we be missing? Astronomer Carl Sagan famously said, "Absence of evidence is not evidence of absence." Just because we haven't detected something doesn't mean it's not there. The Andromeda halo existed for billions of years before we confirmed it. It was always there, invisible yet massive, invisible yet influential, invisible yet real. This brings us to a crucial question. What is this halo made of? Where did it come from? And what is it doing? The gas in Andromeda's halo isn't just sitting there. It's part of an extraordinary recycling system that has been operating for billions of years, regulating star formation and controlling the galaxy's evolution. Understanding this system reveals that galaxies are not static objects, but dynamic, living entities with circulation systems, almost like biological organisms. Let's start with where this gas came from. The story begins 10 billion years ago, when Andromeda was younger, smaller, and far more violent. Young galaxies are stellar factories, forming new stars at rates hundreds of times faster than the Milky Way does today. Each massive star that forms lives fast and dies young, exploding as a supernova within just a few million years. Supernovae are cataclysmic events. In a few seconds, a single exploding star releases as much energy as the sun will emit over its entire 10 billion year lifetime. That energy doesn't just disappear. It heats surrounding gas to millions of degrees and blasts it outward at thousands of kilometers per second. Imagine setting off a firecracker in a swimming pool. The explosion creates a bubble that expands outward, pushing water away. Now imagine millions of firecrackers going off constantly throughout the pool. The entire pool would be churning, with bubbles colliding, merging, and pushing water in all directions. That's what young galaxies are like. This process is called galactic feedback. As stars form, the most massive ones explode, heating and expelling gas from the galactic disk. Some of this gas escapes entirely, lost to intergalactic space. But much of it doesn't have enough energy to fully escape the galaxy's gravity. Instead, it rises above and below the galactic disk like a fountain, creating what's called a galactic fountain flow. Think of it like a fountain in a city park. Water shoots upward, arcs over, and falls back down. In galaxies, gas heated by supernova blasts upward, perpendicular to the galactic disk, cools as it rises, and eventually falls back down, enriched with heavy elements forged in those supernova. But the most energetic expulsions create something more permanent, the halo. Gas blasted to enormous distances, too far to quickly fall back, forms this extended corona. Over billions of years, as Andromeda's star formation rate decreased, as it ran lower on dense gas clouds for making new stars, the violent fountains subsided, and much of the expelled gas settled into this relatively stable halo structure. Astronomer Molly Peoples at the Space Telescope Science Institute has studied galactic halos extensively. Her work reveals that this isn't unique to Andromeda. Virtually all large galaxies have these halos. They're a natural consequence of the galactic life cycle. As Peoples describes it, the halo is like the galaxy's memory of all the stellar generations that lived, died, and enriched the gas with elements heavier than hydrogen and helium. Here's something that will blow your mind. The halo contains enriched gas. Spectrographic analysis shows silicon, carbon, oxygen, nitrogen, and other elements that could only have been created inside stars. This means the gas in Andromeda's halo was once inside stars. Those stars fused hydrogen into helium, helium into carbon, carbon into oxygen, all the way up to iron. Then they exploded, scattering those elements into space. You are made of star stuff, as Carl Sagan memorably said. But so is the galactic halo. That diffuse gas extending more than 1,000,000 light-years from Andromeda was once part of stars that shone when the universe was less than a quarter its current age. But the halo isn't just a fossil. It's an active participant in the galaxy's current evolution. This brings us to what scientists call the galactic baryon cycle, the flow of normal matter through different phases in and around a galaxy. Here's how it works. Gas in the galactic halo slowly cools. As it cools, gravity pulls it inward. It falls back toward the galactic disk, condensing as it descends. When it reaches the disk, it increases the density of gas there, eventually becoming dense enough to collapse under its own gravity and form new stars. Those stars shine for millions or billions of years, depending on their mass. The most massive ones explode as supernova, heating and expelling gas back into the halo. The cycle continues. This cycle regulates how fast galaxies can form stars. Without the halo acting as a reservoir, galaxies would have used up all their gas billions of years ago and stopped forming stars entirely. The halo is both storage and regulator, a cosmic savings account that allows galaxies to maintain modest levels of star formation over billions of years. Astronomer Jessica Work at the University of Washington has been at the forefront of halo research. Her work has shown that the rate at which gas returns from halos to galactic disks roughly matches the rate at which galaxies form stars. This isn't a coincidence. It's a balanced ecosystem. The galaxy feeds itself from its own recycled material. Think of it like a terrarium, a closed ecosystem. Moisture evaporates from soil and plants, condenses on the glass ceiling, and drips back down, watering the plants again. Nothing is lost. Everything circulates. Galaxies work similarly, though the mechanisms are different, and the scales are incomprehensibly larger. But here's where this gets truly profound. The halo gas isn't uniform. It has structure, temperature variations, density variations, velocity structures showing it's moving, rotating, churning. It's not a simple static bubble, but a complex, dynamic structure shaped by billions of years of stellar feedback, gravitational interactions, and potentially encounters with smaller satellite galaxies that Andromeda has consumed over cosmic time. And this brings us to a chilling realization that should fundamentally change how you think about galaxies. Every galaxy is surrounded by the ghosts of its own past. Every galaxy swims in the recycled remnants of billions of dead stars, the ashes of supernova that exploded when Earth was still molten rock, the enriched elements that will someday form future generations of stars and planets. The halo is history made tangible, time made into gas, death made into the seeds of future birth. When you look at a photograph of Andromeda, you're seeing less than 10% of what's actually there. The other 90% is invisible, intangible, yet absolutely essential to everything you can see. Now we come to the part that affects you directly, though you might not realize it yet. Andromeda's halo and the Milky Way's halo are close enough that they may already be interacting. What does this mean? What happens when galactic halos collide? The answer is both reassuring and unsettling. First, the reassuring part. When we say galaxies are colliding, it's not like two cars crashing. Galaxies are mostly empty space. The distances between stars are so vast that even when two galaxies merge, the chances of any two stars actually colliding is essentially zero. It's like throwing two handfuls of sand toward each other in a football stadium and expecting the grains to hit. Stars will pass by each other, their paths bent by gravity, but remaining intact. No Hollywood-style explosions. No Death Star destroying Alderaan scenarios. From the perspective of a planet orbiting a star in one of these galaxies, the merger might be beautiful, a gradually more spectacular night sky, but not immediately dangerous. But the halo merger is a different story. This is where things get interesting and complex. When two galactic halos begin to interact, their diffuse gas doesn't just pass through each other cleanly. Gas has pressure. It can collide, compress, shock, heat up, and create turbulence. Imagine two massive clouds of fog approaching each other. As they meet, they don't stay separate. They mix, swirl, create eddies and flows. That's happening right now, potentially, where the Milky Way's halo meets Andromeda's halo. Astronomer Roland van der Marel at the Space Telescope Science Institute has created detailed simulations of the Milky Way-Andromeda merger. His work, along with contributions from astronomer Sangmo Tony-san, traces the future evolution of this cosmic collision. According to their models, here's the timeline. In about 4 billion years, Andromeda will be close enough that its disk will be visible in our sky as an enormous oval structure, larger than the constellation Orion. The night sky will be transformed. Anyone alive then, not humans as we know them, but whatever species we've evolved into, or whatever artificial intelligences we've created, will witness a sky impossible to imagine today. About 4.5 billion years from now, the visible disks of the galaxies will have their first pass through. They'll swing past each other, massive spiral structures distorted by tidal forces, stretched into long streamers and tails of stars. This won't be a head-on collision, but a glancing blow, a cosmic near-miss that nonetheless completely disrupts both galaxies' structures. But gravity is relentless. After the first pass, the galaxies won't have enough energy to escape each other. They'll swing back. About 6 billion years from now, they'll collide again, more directly this time. The spiral structures will be completely destroyed. Star formation will briefly skyrocket as gas clouds collide and compress. The night sky, if anyone is there to observe it, will blaze with billions of new, blue, young stars. Over the next few billion years, the galaxies will merge completely. The final product, astronomers call it Milkomeda, or sometimes Milkdromeda, will be an enormous elliptical galaxy, no longer a spiral. The organized rotation that created spiral arms will be disrupted. Stars will orbit the galactic center on random paths, creating a roughly spherical distribution. The merged galaxy will be larger than either progenitor, but less structured, more chaotic. And here's what's crucial to understand: this merging process doesn't start 4 billion years from now. The halo interaction may have already begun. The outermost regions of these halos, the thin, diffuse gas more than 1 million light-years from each galactic center, could already be mixing? What does this mean practically? Not much for Earth in the short term. The gas densities involved are so low that you wouldn't notice, even if you could somehow stand in the space between galaxies. We're talking about a few atoms per cubic meter in some regions. For context, the best artificial vacuum ever created still has millions of atoms per cubic meter. The intergalactic gas is far more empty than the best vacuum humans have ever produced. But over millions of years, as the halos interact more substantially, several things might happen. First, shock waves in the gas could trigger star formation. When gas clouds collide and compress, they can reach densities high enough to gravitationally collapse into stars. The halo interaction could seed new generations of stars in unexpected places, not in the galactic disks where star formation normally occurs, but in the outer regions where the halos meet. Second, the mixing of material from two separate galaxies could change the chemical composition of gas throughout both systems. Andromeda and the Milky Way formed independently and have slightly different element abundances based on their different histories. Mixing them creates a more homogeneous chemical environment. Third, and most speculatively, the added turbulence and energy in the halo could affect the rate at which gas falls back onto the galactic disks, potentially slightly increasing or decreasing star formation rates over time. Astronomer Gertina Besla at the University of Arizona has studied how galactic interactions begin. Her research shows that the effects start small and build gradually. Early interactions might be barely noticeable tiny perturbations in gas velocities, slight temperature increases in specific regions. But these small effects compound over time, eventually leading to dramatic transformations. Here's something to consider that should give you chills. Every atom of oxygen you breathe was created inside a massive star that exploded as a supernova billions of years ago. That oxygen was blasted into space, became part of a gas cloud, eventually condensed to form the sun and Earth, and ended up in your lungs. You are intimately connected to the galaxy's history. Now consider that some of those atoms might have come from Andromeda. The halo mixing means there's a non-zero chance that material from our neighboring galaxy has already made its way to Earth. You might be breathing atoms that originated in Andromeda. You might be made partly of Andromedan material. The boundaries are less clear than we thought. The separation less absolute. We are not two distant, separate systems. We are already becoming one. Now we need to address the elephant in the room, or more accurately, the invisible mammoth surrounding the room. The halo of hot gas we've been discussing accounts for a significant amount of Andromeda's missing mass, but it's not the whole story. Not even close. To truly understand how big Andromeda is, we need to talk about dark matter. This is going to challenge everything you think you know about reality. Are you ready? Dark matter makes up about 85% of all matter in the universe. Let that sink in. Everything you can see, everything you've ever touched, every star, planet, gas cloud, and galaxy visible in our telescopes represents only about 15% of the matter that exists. The rest is invisible, undetectable except through its gravitational influence. When scientists say Andromeda extends more than 1 million light-years from its center, they're primarily talking about the extent of its dark matter halo. The visible stars extend about 110,000 light-years from the center. The hot gas halo extends perhaps 1.3 million light-years. But the dark matter? The dark matter halo likely extends even further, possibly 2 million light-years or more from Andromeda's center. Here's what will blow your mind. We don't know what dark matter is. We've known it must exist for over 50 years. We can calculate exactly how much of it there is. We can map where it is based on its gravitational effects. But we have no idea what it's made of. Think about that. The vast majority of matter in the universe, the stuff that holds galaxies together and makes structures like Andromeda possible, is completely unknown to us. It's not made of atoms. It's not made of protons, neutrons, or electrons. It might be exotic particles that have never been detected in laboratories. It might be something stranger than we can currently imagine. The evidence for dark matter is overwhelming. Let me walk you through some of the key pieces. First, there's Vera Rubin's rotation curve observations I mentioned earlier. When she measured how fast stars orbit around galactic centers, the speeds were far too high to be explained by the visible mass alone. The outer stars should fly away into intergalactic space unless there's additional mass providing extra gravity. That mass is dark matter. Second, gravitational lensing. Einstein's general relativity tells us that mass bends spacetime, and light follows curved spacetime. So massive objects act like lenses, bending light from objects behind them. When astronomers observe distant galaxies behind galaxy clusters, they see the light distorted, stretched into arcs, and sometimes complete rings called Einstein rings. By measuring the distortion, they can calculate how much mass is doing the lensing. Consistently, the lensing mass is about 6 times larger than the visible mass. That extra mass is dark matter. Third, the bullet cluster observation. In 2006, astronomers observed 2 galaxy clusters that had collided and passed through each other. The normal matter, stars and hot gas, slowed down due to friction and collision. But gravitational lensing showed that most of the mass had passed right through without slowing. The mass and the normal matter separated. This is exactly what you'd expect if most of the mass is dark matter, which doesn't collide or interact except through gravity. Fourth, the cosmic microwave background. This is radiation left over from the Big Bang, a snapshot of the universe when it was only 380,000 years old. Tiny temperature variations in this radiation tell us about density variations in the early universe. The pattern of these variations only makes sense if the universe contains roughly 85% dark matter and 15% normal matter. Independent confirmation from the universe's baby picture. For Andromeda specifically, astronomers have mapped the dark matter halo using several techniques. One involves measuring the velocities of satellite galaxies orbiting Andromeda. These small galaxies, like M32 and M110, orbit in Andromeda's gravitational field. By measuring their speeds and distances, scientists can calculate how much mass must be present to keep them in orbit. The answer is far more than the visible stars and gas can account for. Another technique involves studying stellar streams along rivers of stars stretched out around Andromeda. These are the remnants of small galaxies that Andromeda's gravity has torn apart. The shapes and positions of these streams are sensitive to the distribution of dark matter. By modeling the streams and comparing them to observations, astronomers can map where the dark matter is. What they found is that Andromeda sits in the center of an enormous dark matter halo, roughly spherical, extending possibly 2 million light-years from the galactic center. This halo contains several times more mass than all the visible stars in the galaxy. It's the foundation, the gravitational architecture that allows the visible galaxy to exist. Now here's where this gets truly mind-bending. Dark matter particles, whatever they are, don't collide with each other or with normal matter, except through gravity. This means right now, as you read this, dark matter particles are passing through your body, trillions of them every second. They pass through the Earth, through the sun, through everything, without interacting at all. You are swimming in dark matter. Your body exists in a sea of invisible particles that outnumber normal atoms by a factor of 6. They're everywhere, all around you, passing through you, completely undetectable except in the aggregate where their gravity becomes noticeable. The Milky Way has its own dark matter halo. Andromeda has its dark matter halo. And these halos, like the gas halos, extend far beyond the visible galaxies. They're likely already overlapping. Dark matter from Andromeda surrounds our solar system. Dark matter from the Milky Way surrounds Andromeda. Astronomer Catherine Fries at the University of Texas at Austin has spent her career studying dark matter. She's proposed several candidates for what dark matter might be. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, or something else entirely. Despite decades of searching with increasingly sensitive detectors, we haven't directly detected dark matter particles yet. This creates an uncomfortable philosophical question. What does it mean to say something exists if we can't detect it? We infer dark matter's existence from its effects, but we've never seen or touched it. It's like concluding that wind exists because you see trees swaying, even though you can't see the wind itself. But the evidence is so overwhelming that essentially no mainstream astronomer doubts dark matter's existence. The alternatives modifying our laws of gravity have consistently failed to explain observations as successfully as dark matter does. So when we say Andromeda is more than 1 million light-years across, we're making a statement about gravitational influence. We're saying that Andromeda's mass visible and invisible affects objects out to at least that distance. The galaxy's gravity extends far beyond what we can see, shaping the motions of satellites, bending spacetime, and defining a region of space that belongs to Andromeda. This raises a profound question. What is a galaxy, really? Is it the stars we can see? Is it all the normal matter, including the diffuse gas halo? Or is it the full extent of the dark matter halo, the gravitational structure within which everything else exists? Most astronomers would say the complete answer is the latter. A galaxy is ultimately defined by its gravitational influence, by the extent of its dark matter halo. The visible stars and gas are just tracers, lights that allow us to see where the underlying dark structure is. Andromeda is so much more than a spiral of stars. It's a massive gravitational well, a concentration of dark matter that collected normal matter and allowed it to form stars and planets. The visible galaxy is the symptom. The dark matter halo is the disease, or rather, the cause, the foundation, the real entity. And that foundation, that dark structure, extends further than we ever imagined, and is likely already touching our own. Let's get technical for a moment, because the methods scientists use to measure these invisible halos are so clever they deserve appreciation. This is detective work on a cosmic scale, using physics and ingenuity to reveal what can't be directly seen. The key technique, as I mentioned, is called absorption spectroscopy using background quasars. But let me explain just how sophisticated this technique has become, because it's honestly one of the most impressive achievements of modern astronomy. A quasar is a supermassive black hole at the center of a distant galaxy, actively feeding on material. As matter spirals into the black hole, it heats to millions of degrees and radiates across the entire electromagnetic spectrum radio waves: infrared, visible light, ultraviolet, X-rays. Quasars are the most luminous persistent objects in the universe. A single quasar can outshine an entire galaxy of 100 billion stars. These quasars are billions of light years away. Their light has traveled for billions of years to reach us. And here's the key. Along that journey, the light passes through everything between the quasar and Earth. It passes through intergalactic space, through galactic halos, through gas clouds. Every time it encounters material, atoms in that material absorb specific wavelengths. Think of white light passing through a prism. The prism splits the light into a rainbow. Similarly, when astronomers pass quasar light through a spectrograph, they split it into its component wavelengths. Then they look for dark lines, absorption lines, where specific wavelengths are missing. Each element creates a unique pattern of absorption lines, like a barcode. Hydrogen absorbs specific wavelengths. Silicon absorbs different specific wavelengths. Oxygen, nitrogen, carbon each has its signature. By identifying which absorption lines are present, astronomers can determine which elements the light encountered. But it gets better. The wavelength of these absorption lines tells you how fast the absorbing material is moving. This is called the Doppler shift. Light from objects moving toward you is blue shifted toward shorter, bluer wavelengths. Light from objects moving away is red shifted toward longer, redder wavelengths. The width of the absorption lines tells you the temperature of the gas. Hotter gas has atoms moving faster in random directions, which broadens the absorption line. Cooler gas has narrower lines. The strength of the absorption, how much light is absorbed, tells you the density of the gas. More atoms in the light's path means more absorption. So from a single spectrum of a single quasar, astronomers can determine what elements are present, how hot the gas is, how dense it is, and how fast it's moving. That's an extraordinary amount of information from patterns of dark lines on a spectrum. Nicholas Lenner's team observed 43 quasars positioned behind different parts of Andromeda. Each quasar's spectrum told them about the halo gas at that specific location. By combining all 43 observations, They built up a three-dimensional map of the halo's properties. They found that the halo isn't uniform. It has structure. The gas is hotter in some regions than others. It's denser in some places. It's moving faster in certain directions. This structure tells a story about the halo's history, about past supernova and stellar feedback events that shaped it. One particularly clever aspect of this work involved distinguishing between gas in Andromeda's halo and gas that might be in the Milky Way's halo, or even in intergalactic space between the galaxies. How do you know which galaxy the gas belongs to? The answer lies in velocity. Gas that belongs to Andromeda should be moving with Andromeda sharing its rotation and motion through space. By measuring the Doppler shifts carefully, astronomers can identify which absorption lines are at velocities consistent with Andromeda's motion and which might be from other sources. Samantha Barrick and her colleagues took this work further. They specifically looked at the hot gas in the 100,000 to 1 million degree temperature range. This gas absorbs ultraviolet light at specific wavelengths corresponding to highly ionized oxygen and nitrogen. These ions only exist at these high temperatures, so detecting them is proof that the gas is hot. They found this hot gas extends even further than the cooler gas detected in earlier studies, reaching at least 1.3 million light-years from Andromeda's center. This makes sense theoretically. Hotter gas has more energy and can reach greater heights above the galactic disk before cooling and falling back. But here's the challenge that makes this work so difficult. To observe ultraviolet absorption lines, you need a space telescope. Earth's atmosphere blocks most ultraviolet light, which is good for us. We'd be fried by UV radiation otherwise, but bad for astronomers studying hot gas. The Hubble Space Telescope, with its cosmic origin spectrograph instrument, is perfectly suited for this work. However, telescope time is precious. Hubble is one of the most sought-after instruments in astronomy. Thousands of proposals compete for observing time each year. Only the most compelling projects get approved. Lehner's and Barrick's teams had to write detailed proposals explaining why this work was important, what they would observe, and what they expected to find. Then they had to execute the observations flawlessly. A single mistake could waste hours of irreplaceable telescope time. Think about the precision required. They're measuring the absorption of light from objects billions of light-years away. Absorption caused by gas that's 2.5 million light-years away, gas so diffuse that there's barely anything there. They're detecting the shadows cast by nearly nothing on light that has traveled for most of the universe's history. And from these shadows, these faint traces, they've reconstructed the structure of an invisible halo larger than anyone imagined. This is human ingenuity at its finest. This is what we can accomplish when we apply our intelligence, creativity, and persistence to understanding nature. We've revealed the invisible through cleverness and careful observation. But even with these spectacular measurements, uncertainties remain. The halo's exact outer edge is still unclear. Does it fade gradually to nothing, or is there a more defined boundary? How does the halo structure change with direction? Is it spherical or elliptical? How much mass is in the halo compared to the visible galaxy? These questions drive ongoing research. Teams around the world are observing more quasars, developing better analysis techniques, creating more sophisticated computer simulations. Each new observation refines our understanding. This is how science progresses, not through sudden revolutions, though those do happen occasionally, but through the accumulation of careful measurements that gradually reveal truth. And the truth about Andromeda is that it's vastly larger, vastly more complex, and vastly more magnificent than we realized. All right, let's address the question I know has been building in your mind. What does this mean for Earth? For humanity? For you personally? Are we in danger? The short answer is no immediate danger whatsoever. But the long-term implications are both fascinating and sobering. First, the timeline. The visible disk-to-disk collision won't occur for approximately 4.5 billion years. To put that in perspective, Earth is 4.54 billion years old. The time until the collision is roughly equal to all of Earth's history so far. That's a staggeringly long time. In 4.5 billion years, the Sun will have aged significantly. It's currently about halfway through its main sequence lifetime. In 4.5 billion years, it will be nearing the end of its normal life. It will be noticeably brighter and hotter. Earth's oceans will likely have evaporated. The planet will be approaching the end of its habitable period, if it hasn't already ended. So the Andromeda Milky Way merger will occur around the same time that Earth is becoming uninhabitable due to the Sun's aging. These are both endgame scenarios for life on Earth, as we know it. But let's assume for a moment that some remnant of humanity survives, perhaps on colony worlds around other stars, perhaps in artificial habitats in space, perhaps as uploaded consciousnesses in computers. What would these beings experience during the merger? Astronomer Roland van der Marel created detailed simulations. Here's what happens. Starting around 4 billion years from now, Andromeda becomes increasingly prominent in the night sky. Currently, it's visible as a faint fuzzy patch. In 4 billion years, it will dominate the sky, a massive spiral disk visible to the naked eye in stunning detail. During the first close approach, about 4.5 billion years from now, Andromeda would fill half the sky. The spiral arms would be clearly visible, individual bright stars resolvable. It would be simultaneously beautiful and terrifying, a reminder of the immense gravitational forces at work. As the galaxies pass through each other, the night sky would become incredibly chaotic. Stars from both galaxies mixed together, long streamers and tails of stars pulled out by tidal forces. Intense bursts of star formation, creating brilliant blue clusters of young stars. The sky would change noticeably over millions of years, fast on cosmic timescales, though still far too slow to see motion in real time. But here's the crucial point. Even though the galaxies are colliding, the Sun and its planets, or what remains of them, are unlikely to be directly affected in a catastrophic way. The probability of another star passing close enough to our solar system to gravitationally disrupt the planets is very small, though not zero. Computer simulations suggest there's about a 12% chance the Sun will be pulled out of the galactic disk entirely and flung into the outer halo of the merged galaxy. This would be disorienting from an observational standpoint. The Milky Way's disk would no longer surround us, but wouldn't directly harm planetary systems. There's a roughly 3% chance the Sun could be ejected from the merged galaxy entirely, flung into intergalactic space. Again, this sounds dramatic, but from the perspective of someone on a planet orbiting the Sun, not much would change locally. The Sun would keep shining. Planets would keep orbiting. The only difference would be an incredibly lonely, dark night sky devoid of the bright backdrop of the galactic disk. The far more likely scenario, about 85% probability, is that the Sun remains within the merged galaxy, probably settling into an orbit in the outer regions of the new elliptical galaxy. The night sky would eventually stabilize, though it would look nothing like the night sky we see today. Astronomer Jay Gallagher at the University of Wisconsin-Madison has studied galactic mergers extensively. He points out that during the merger, there will be a temporary spike in star formation. Gas clouds from both galaxies will collide, compress, and form new stars at rates potentially 10 to 100 times higher than current levels in either galaxy. This means any civilizations alive during the merger would witness an incredible golden age of star. Birth new stars lighting up across the sky, stellar nurseries visible in unprecedented teal. But there's a darker side. The merger will also disrupt planetary systems, not through direct collisions, but through gravitational perturbations. When massive clouds and clusters pass near star systems, their gravity can disturb the orbits of objects in the outer solar system comets, asteroids, Kuiper belt objects. This could send swarms of comets into the inner solar system, increasing the risk of impacts on inner planets. Some estimates suggest the impact rate could increase by a factor of 10 or more during the most chaotic phases of the merger. This could be catastrophic for any surviving biospheres. However, by 4.5 billion years from now, Earth's natural biosphere will already be gone due to the Sun's evolution, so this is only relevant for any artificial biospheres or colonies that might exist. There's also the question of the supermassive black holes. Both the Milky Way and Andromeda have supermassive black holes at their centers. The Milky Way's black hole, Sagittarius A*, has a mass of about 4 million times the Sun. Andromeda's black hole is much larger, about 100 million solar masses. When the galaxies merge, these black holes will eventually sink to the center of the merged galaxy and themselves merge. This merger will release tremendous energy in the form of gravitational waves ripples in space-time itself. For a brief period, perhaps lasting a few hours, this black hole merger will be the single most energetic event in the local universe, releasing more energy than all the stars and millions of galaxies combined. However, this energy is released as gravitational waves, not electromagnetic radiation. Gravitational waves pass through matter without interacting much, so even though the energy release is enormous, it won't directly affect planets or life. But it would be detectable. Any gravitational wave detectors operating at that time would register the most spectacular signal ever recorded. Perhaps most profound is this: the merger will create something new. Milkomeda, the merged galaxy, will be fundamentally different from either progenitor. It will be larger, more massive, and structurally distinct. The beautiful spiral arms that characterize both the Milky Way and Andromeda will be destroyed, replaced by the more disordered structure of an elliptical galaxy. Some astronomers find this sad. Spiral galaxies are arguably more beautiful than elliptical galaxies, but others see it as a natural part of the cosmic cycle. Galaxies are not eternal, unchanging objects. They evolve, grow, merge, and transform. What we see now is just a snapshot in a much longer story. And here's something to make you feel small and large at the same time. This merger happens because of dark matter. The dark matter halos of these two galaxies have been gravitationally attracting each other for billions of years. What happens to visible matter stars, planets, is almost incidental. The real story is the slow dance of invisible dark matter halos, gradually drawing closer, their mutual gravity making the merger inevitable. You are a passenger in a cosmic process driven by invisible forces you can barely detect, creating changes on timescales incomprehensible to human experience, leading to a future unlike anything that has existed before. At this point, you might be wondering, is Andromeda special? Or do all large galaxies have these enormous, previously unrecognized halos? The answer will blow your mind. They all do. Every single large galaxy we've studied carefully enough shows evidence of extended halos. Andromeda just happens to be close enough and bright enough that we could study it in unprecedented detail. It's not an exception. It's the rule. Think about what this means. Every spiral galaxy you've ever seen in a photograph is surrounded by an invisible halo, potentially 10 times larger than the visible disk. Every elliptical galaxy sits within a massive corona of hot gas and dark matter. The universe is much more full, much more connected, much less empty than images suggest. Astronomer Jason Tomlinson at the Space Telescope Science Institute led a major project called the Cosmic Origins Spectrograph Guaranteed Time Observations Program. This team systematically studied the halos of multiple galaxies using the same quasar absorption technique that revealed Andromeda's halo. What they found was consistent. Large star-forming galaxies have massive hot halos. Galaxies that have stopped forming stars, quenched galaxies, have different halo properties, less gas, often cooler. The halo structure appears to be connected to the galaxy's evolutionary state. Young, actively star-forming galaxies have halos fed by ongoing stellar feedback supernova-driven winds, continuously pushing material out. These halos are hotter and more dynamic. Older, quieter galaxies have halos that are more settled, with less active circulation. And 31, Andromeda, is somewhat intermediate. It's still forming stars, but at a relatively low rate compared to younger, more active galaxies. Its halo reflects this massive and extended, but not as violently turbulent as halos around starburst galaxies. The most extreme examples of galactic halos are around starburst galaxies forming stars at rates 100 to 1,000 times faster than the Milky Way. These galaxies have superwinds, enormous outflows of hot gas, blasting outward at thousands of kilometers per second. The galaxy M82 is a famous example. It's relatively nearby at about 12 million light-years, and Hubble images clearly show vast plumes of gas extending far above and below the galactic disk. These superwinds are powered by the combined energy of thousands of supernova and massive stars. The scale is difficult to comprehend. A single supernova releases about 1051 ergs of energy. That's a 1 followed by 51 zeros in units of ergs. A typical starburst galaxy might experience hundreds of supernova per century. The cumulative energy is enough to blow material completely out of the galaxy. Where does this material go? Some escapes into intergalactic space, enriching the intergalactic medium with elements forged in stars. But much of it forms an extended halo, eventually cooling and falling back to fuel future star formation, the galactic fountain I described earlier. This process of material circulation is called the baryon cycle, baryons being the normal matter made of protons and neutrons. Understanding this cycle is one of the major goals of modern astrophysics because it controls how galaxies grow and evolve over cosmic time. Here's something that should give you pause. The gas in these halos has been on an incredible journey. Consider a single oxygen atom in Andromeda's halo. That atom was forged inside a massive star that lived 10 billion years ago. The star fused helium and carbon nuclei together, creating oxygen through nuclear fusion. After a few million years, the star exploded as a supernova, blasting that oxygen atom into space at thousands of kilometers per second. The atom joined a hot bubble of supernova ejecta, mixing with material from thousands of other supernova explosions. Over millions of years, this hot bubble rose above the galactic disk, expanding and cooling. Eventually, it reached hundreds of thousands of light years above the disk, becoming part of the extended halo. For billions of years, that oxygen atom drifted in the halo, slowly cooling, occasionally colliding with other atoms in the diffuse plasma. Gradually, gravity began pulling it back toward the galactic disk. Over tens of millions of years, it fell inward, joining a cool molecular cloud. The cloud collapsed under its own gravity, forming new stars. That oxygen atom might now be locked in a rocky planet orbiting one of those stars, perhaps in an atmosphere, perhaps in the crust. Or it might still be in the halo, one of the atoms that Leonard's team detected through absorption spectroscopy. Either way, it has been on a journey spanning billions of years and millions of light years, from the heart of a star to the outer reaches of the galaxy, and potentially back again. Every atom of heavy elements in the universe has a similar story. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it was forged in stars, expelled in supernova explosions, and spent time in galactic halos before eventually finding its way into the molecular cloud that collapsed to form our solar system. You are made of material that has been on cosmic journeys. You are recycled stardust, elements that have cycled through multiple generations of stars, through galactic halos, through space and time. Now apply this understanding to the universe as a whole. There are an estimated 200 billion to 2 trillion galaxies in the observable universe. If each large galaxy has a halo extending potentially 1 million light-years or more, the amount of material in galactic halos is staggering. Some estimates suggest that galactic halos contain more baryonic, normal, matter than all the stars in all the galaxies combined. This material is difficult to study because it's so diffuse and hot, emitting primarily in ultraviolet and X-ray wavelengths that are absorbed by Earth's atmosphere. It requires space-based observatories and clever techniques to detect. But it's there, a vast reservoir of material that plays a crucial role in cosmic evolution. The discovery of Andromeda's extended halo is part of a larger revolution in understanding galaxy structure. We're realizing that the bright, photogenic parts of galaxies, the parts that appear in Hubble images and astronomy posters, are just the tip of the iceberg. The bulk of this structure is invisible, revealed only through sophisticated observations and analysis. This has profound implications for cosmology. The amount of normal matter in the universe was calculated from Big Bang nucleosynthesis theory and confirmed by observations of the cosmic microwave background. But when astronomers added up all the normal matter they could see, stars, gas clouds, planets, they came up short. A lot of normal matter was missing. Where was it? A significant fraction, perhaps 30 to 40%, turns out to be in galactic halos and the intergalactic medium, invisible to traditional observations. The discovery of extended galactic halos solved a significant piece of the missing baryon problem. There's still some normal matter unaccounted for, thought to be an extremely diffuse, warm-hot intergalactic gas, but the gap has narrowed considerably thanks to halo observations. This illustrates a crucial principle in science. When observations don't match theoretical predictions, something is wrong. Either the theory is wrong, or the observations are incomplete. In this case, the observations were incomplete. The matter was there all along. We just weren't looking in the right way. How many other missing things in astronomy are simply invisible, waiting for the right technique to reveal them? This question drives ongoing research and motivates the development of new telescopes and instruments. The universe is stranger and more complex than it appears. Every time we develop a new way of looking, we find something unexpected. Every time we push our instruments to greater sensitivity, we reveal structures we didn't know existed. Andromeda's enormous halo is not an anomaly. It's a window into the true structure of all large galaxies, including our own. Let's zoom out and look at the bigger picture. Andromeda and the Milky Way aren't alone. They're part of a collection of galaxies called the Local Group, and understanding the true sizes of these galaxies forces us to completely reimagine our cosmic neighborhood. The Local Group contains more than 50 galaxies. Most are small dwarf galaxies, tiny compared to the Milky Way and Andromeda. But the structure of the Local Group is dominated by 3 large galaxies: Andromeda, the largest, the Milky Way, second largest, and the Triangulum Galaxy, or M33, a distant third but still substantial. Traditionally, astronomers thought of the Local Group as a region about 10 million light-years across, with galaxies spread throughout this volume more or less evenly. The Milky Way and Andromeda were the 2 major gravity wells, each with their own collection of satellite dwarf galaxies. But if Andromeda's halo extends 1.3 to 2 million light-years from its center, and the Milky Way's halo extends roughly 0.5 to 1 million light-years from its center, and the 2 galaxies are separated by about 2.5 million light-years, the geometry of the Local Group is completely different than we thought. The halos are nearly touching or may already overlap. This means there isn't really empty space between the galaxies. There's a continuum of decreasing density from Andromeda's core to its outer halo, through a potential overlap region, into the Milky Way's outer halo, and down to the Milky Way's core. It's more like a barbell, 2 dense cores connected by a less dense but continuous bridge of material. What about the smaller galaxies? How do they fit into this picture? Triangulum Galaxy, M33, is located about 2.7 million light-years from the Milky Way and somewhat closer to Andromeda. It's a beautiful spiral galaxy, the third largest in the local group, with about 40 billion stars, compared to the Milky Way's 200 to 400 billion and Andromeda's 1 trillion. And 33 is actually close enough to Andromeda that it might be a satellite galaxy, gravitationally bound to Andromeda rather than an independent structure. Recent observations suggest M33 may have already passed through or near Andromeda's halo at some point in the past. Tidal distortions in M33's structure hint at a close encounter. This raises the possibility that M33 will eventually be consumed by Andromeda, merging into the larger galaxy before the Milky Way-Andromeda collision even occurs. Then there are the dwarf galaxies. The Milky Way has dozens of satellite dwarf galaxies, including the large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches in the night sky. Andromeda has even more satellites, with over 30 identified and probably many more waiting to be discovered. These dwarf galaxies orbit their host galaxies like planets orbit the Sun, held in place by gravity. But if the halos of the host galaxies extend so far, many of these dwarf galaxies are actually orbiting within the halos of their hosts. They're not in empty space, circling a distant object. They're embedded in the outer reaches of the larger galaxy's structure. This changes how we think about satellite galaxies. They're not separate entities, but integrated parts of a larger system. They're orbiting within the halo, swimming through diffuse gas, potentially interacting with halo material as they move. Some dwarf galaxies show evidence of ram pressure stripping, their own gas being stripped away by their motion through the halo gas of the host galaxy. Think of it like a meteor entering Earth's atmosphere. The meteor is moving through air, and friction with air molecules heats the meteor and strips away its outer layers. Similarly, a dwarf galaxy moving through a galactic halo can have its gas stripped away by the friction of moving through the diffuse halo gas. This gas stripping can affect the dwarf galaxy's ability to form new stars. Without gas, star formation stops. Over time, ram pressure stripping can transform a gas-rich, star-forming dwarf galaxy into a gas-poor relic containing only old stars. Astronomer Gertina Besla, who I mentioned earlier, has studied the Magellanic Clouds extensively. Her work suggests that the large Magellanic Cloud is undergoing ram pressure stripping right now as it moves through the Milky Way's halo. A stream of gas has been pulled from the large Magellanic Cloud, stretching across the sky in a massive arc called the Magellanic Stream. This stream is visible in radio wavelengths and extends more than 200 degrees across the sky that's more than twice the width of the Big Dipper. The Magellanic Stream is direct evidence of halo interactions. It's proof that dwarf galaxies don't exist in isolation, but are actively interacting with the halos of their host galaxies. Now, project this understanding across the local group. Every satellite galaxy is potentially interacting with its host's halo. Material is being exchanged. Gas is being stripped and redistributed. The boundaries between galaxies are fuzzy and dynamic, not clean and static. The local group is less like a collection of separate islands and more like an ecosystem, with material and energy flowing between components, everything connected through halos and gravitational interactions. And here's something that should make you reconsider cosmic isolation. Other galaxy groups exist beyond the local group. The nearest significant group is the Virgo cluster, about 50 million light-years away, containing over 1,500 galaxies. If every large galaxy in the Virgo cluster has a halo extending 1 million light-years or more, those halos are overlapping throughout the cluster. The entire Virgo cluster might be permeated by a diffuse, hot intracluster medium, with individual galaxies as density peaks within a continuous structure. At the largest scales, galaxy superclusters, collections of clusters, are connected by filaments of dark matter and gas, forming the cosmic web. This large-scale structure is the backbone of the universe, with galaxies forming along dark matter filaments like beads on a string. The discovery of extended galactic halos fits into this bigger picture. Galaxies aren't isolated systems. They're nodes in a cosmic network, connected by halos, by gravitational interactions, by the flow of material along dark matter filaments. The universe is more interconnected than we realized. The spaces between galaxies aren't empty voids, but transition zones where one galaxy's influence fades and another's begins. On the largest scales, the universe is a single interconnected structure. Boundaries are artificial, defined by human preference for categorization. The reality is more fluid, more continuous, more unified. You live in a galaxy that extends far beyond what you can see. Your galaxy is already touching its nearest neighbor. Your cosmic neighborhood is a tangled web of overlapping halos and gravitational influences. You are part of a structure that spans tens of millions of light years, connected to it all through gravity and the shared history of cosmic evolution. The universe is not a collection of separate things. It's a continuous whole, and we're just beginning to understand the full extent of its interconnection. Understanding Andromeda's halo isn't just about observations. Some of the most important insights come from computer simulations. And these simulations are so sophisticated, so computationally demanding, that they require some of the world's most powerful supercomputers. Let me take you inside the world of cosmological simulations, because what scientists have created is nothing short of building artificial universes to understand our own. The challenge is this: you can't watch a galaxy evolve in real time. Galactic evolution occurs over billions of years. You get one snapshot of each galaxy, you observe the present moment. To understand how galaxies form and develop their halos, you need to simulate the process. This requires solving equations that govern gravity, gas dynamics, star formation, supernova feedback, dark matter behavior, and more. For millions or billions of particles representing stars, gas clouds, and dark matter, over billions of years of simulated time. One of the most ambitious projects is called Illustris, led by a team including Mark Vogelsberger at MIT and Deborah Szyatski at Cambridge. Illustris simulated a cube of the universe, 106.5 million light-years on each side, containing about 12 billion resolution elements, particles representing dark matter and gas, tracked over 13.8 billion years of cosmic history, from shortly after the Big Bang to the present day. The simulation ran on supercomputers and required millions of CPU hours. The amount of data generated was enormous, hundreds of terabytes. But the result was unprecedented. A fully three-dimensional, evolving model of how galaxies form, grow, merge, and develop their halos.